Hey guys, welcome back to my channel where we explore interesting math problems. Today, we'll be looking at a geometry problem with some trigonometry and polynomials incorporated into it. So the question reads, in the diagram shown below, AB equals CD equals 1, angle ABC equals 90 degrees, angle CBD equals 30 degrees. What is the length of AC? So since we are given some angles and some side lengths, we could potentially use trigonometry to solve it. One useful trigonometry law that we could use in this case is the law of sine. And one such equation that you can make with triangle ABD is this. Sine of D over BA is equal to sine of B over AD. Notice that while there are other equations that we can make with triangle ABD, like sine of B over AD is equal to sine of A over BD. We choose this one specifically because, as you will see, it relates the length that we're interested in, namely AC. Okay, so substituting in the known values, we know that BA equals 1 and that angle B is 120 degrees since it's 30 degrees plus a right angle 90 degrees. And for AD, the reason why we break it down to AC plus 1 is because we want to find AC. So we will want to isolate it to solve for it later. Further simplifying, we get this. Now, since we want to solve for AC, we want to get rid of sine of D to only have AC in the equation. And one way to do this is to look for other equations you can make using the law of sine by looking at this smaller triangle, DCB, since it has the angle D here that we want to get rid of and replace with something that we can work with. There's actually two equations you can make with angle D inside, but either by trial and error or by observation, you'll find that one of them is much easier for our purposes. Specifically, this, sine of D over BC is equal to sine 30 over DC. Substituting in the known values like last time, we get this. And since we want to get rid of sine of D, we isolate it by multiplying both sides by BC and get this equation with sine of D isolated on one side. Now that we have two equations with sine of D, we can substitute one into the other to get rid of it. And we get square root of 3 over 2 multiplied by AC plus 1 is equal to BC over 2. Now, you might think that we got rid of one unknown value, sine of D, only to get another unknown value, length BC. But actually, because triangle ABC here is a right triangle, using the Pythagorean Theorem, we can get BC in terms of AC by saying that BC is equal to the square root of AC squared minus 1 squared. If you find that the substitution was a bit too sudden, here's a quick explanation. Basically, from the Pythagorean Theorem, we know that BC squared plus 1 squared is equal to AC squared. To solve for BC, we subtract 1 squared from both sides, then take the square root to get BC is equal to the square root of AC squared minus 1 squared. Okay, back to our original equation. We can simplify it by getting rid of the 2 in both denominators and get this equation with only the variable AC inside. To make it easier to solve for AC, we can let some variable k stand for AC. Then, this equation would become square root of 3 over k plus 1 is equal to the square root of k squared minus 1 squared. Now we can solve for k. Multiplying both sides by k plus 1, we get this. Then, to get rid of this inconvenient square root sign, we square both sides. Then we simplify. Since 1 squared is just 1, we can rewrite it as 1, and for the k plus 1 here, we can expand it. Now we just have to multiply the 2 together to fully expand this equation. We can do that by having k squared multiplied by this part here, minus 1 multiplied by the same part. Simplifying, we have this. And subtracting 3 from both sides, we get this final equation where a polynomial with the variable k is equal to 0. To find k, we simply have to factor this equation as much as we can. One way to do this is by synthetic division. It's a lot like long division, but boiled down to its essence. If you don't know what it is, I encourage you to search online or look at the links I attached down below for your reference, since the idea behind it is pretty simple. Either way, when you try this, you might have to do quite a few to find one that works, but I'll just go ahead and show you the one and only one that will work, which is -2. And I'll simply show the processes of synthetic division without explaining. Since you get a 0 here, we know that -2 is indeed a root of this polynomial. This means that the polynomial up here is equivalent to k cubed minus 2 multiplied by k plus 2. And you'll notice that k cubed minus 1 can't be factorized any further, so this is the most that we can go. With this factored equation, we can solve for k by looking at two cases: when k cubed minus 2 is equal to 0, or when k plus 2 is equal to 0. Solving for the first case, we get k is equal to the cube root of 2. Now solving for the second case, we get that k is equal to -2. But wait, k stands for the length AC, and no length could ever have a negative value. Therefore, we reject the solution, which leaves only the possibility that k is equal to the cube root of 2. And remember, k is actually equal to AC. So we now have the final answer that AC is equal to the cube root of 2.